Hey everyone, welcome back to the channel. Today, we're tackling one of the biggest questions you can possibly ask. What is the cosmos? Now, I know what you're thinking. You've heard the word thrown around, maybe in science class, maybe in a documentary, or maybe you just think it sounds cool. And you're right, it does sound cool. But it's so much more than just a fancy word for space. So, grab a coffee, get comfortable, because for the next hour, we're going on a journey. We're going to explore everything from the tiniest particles to the largest structures in existence. We're going to talk about time, space, matter, energy, and how it all fits together into this mind-blowing thing we call the cosmos. Let's dive in. So first things first, what actually is the cosmos? The simplest answer? The cosmos is everything. And I mean everything. Every star you see at night, every planet, every galaxy, every bit of empty space between them. Your coffee mug, your phone, your body, the air you're breathing right now. All of it. The cosmos is the entire universe and everything in it, treated as one complete, interconnected system. But here's where it gets interesting. The word cosmos doesn't just mean stuff existing. It carries this deeper meaning. It comes from the ancient Greek word meaning order or harmony. The Greeks looked up at the night sky, and instead of seeing chaos, they saw patterns, they saw order, they saw beauty. And that's what makes the cosmos different from just saying universe. When we say cosmos, we're not just listing things that exist. We're talking about how everything fits together, how the laws of physics apply everywhere, how galaxies form patterns, how atoms behave the same way on Earth as they do in a star billions of light years away. The cosmos is the universe, but it's the universe understood as an organized, comprehensible whole. It's saying that reality follows rules, and those rules make sense. Pretty wild when you think about it, right? Now, humans have been trying to understand the cosmos for thousands of years. Ancient civilizations built entire belief systems around it. They created myths to explain the sun and moon. They tracked the planets with incredible precision. They wondered about their place in all of it. And we're still doing the same thing today. We've just got better tools. All right, let's talk about scale, because this is where things get absolutely bonkers. Start with yourself. You're probably somewhere between 5 and 6 feet tall. That's your scale. Now, zoom out. Your city might be 10, 20, 50 miles across. Your country could be thousands of miles wide. Earth itself, about 8,000 miles in diameter. Already we're at scales that are hard to really grasp. Like, you can't walk across a continent. You can't really imagine 8,000 miles in a visceral way. But we're just getting started. The moon is about 240,000 miles away. The sun is 93 million miles from Earth. We call that distance an astronomical unit because it's so useful for measuring things in space. But even that becomes tiny when you zoom out further. Neptune, the farthest planet in our solar system, is about 30 astronomical units from the Sunday. That's roughly 2.8 billion miles, a billion with a B. Light, which is the fastest thing in the universe, takes over 4 hours to reach Neptune from the Sunday. And our solar system? It's a speck, a tiny dot in a galaxy called the Milky Way. The Milky Way contains somewhere between 100 and 400 billion stars, billion, each one potentially with its own planets. The galaxy is about 100,000 light-years across. That means if you could travel at the speed of light, it would take you 100,000 years to cross it. The nearest major galaxy to us, Andromeda, is 2.5 million light-years away. The light we see from Andromeda today left there before humans existed. But even galaxies cluster together. Our local group contains about 80 galaxies. That's part of a larger structure called the Virgo supercluster. And that's part of an even larger structure called Laniakea, which contains 100,000 galaxies. And beyond that, more superclusters, more galaxies, more stars, more planets. The observable universe, the part we can actually see, is about 93 billion light-years in diameter. Let me say that again, 93 billion light-years. And that's just what we can observe. The actual universe could be infinitely larger. We literally don't know. The scale of the cosmos is so vast that it breaks our brains. We didn't evolve to comprehend distances like this. We evolved to hunt, to gather, to navigate forests and plains, not to imagine billions of light years. But here's the beautiful thing. Even though we can't truly grasp these scales, we can understand them. We can measure them. We can study them. And that's kind of amazing. So we've talked about how big the cosmos is. Now let's talk about what's actually in it. And this is where things get weird, because most of the cosmos isn't what you think it is. Let's start with the stuff we can see and touch. Regular matter, atoms, you, me, stars, planets, dust, gas, all the stuff that makes up everyday reality. This is called baryonic matter in physics terms. And here's the kicker. It only makes up about 5% of the cosmos. 5%. So what's the other 95%? About 27% is something called dark matter. Now, dark matter is one of the biggest mysteries in science. We can't see it. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all. So how do we know it exists? Gravity. When we observe galaxies spinning, they rotate way too fast. Based on the visible matter alone, they should fly apart. But they don't. Something else is holding them together. Something with mass that creates gravitational pull. We call it dark matter because we're literally in the dark about what it is. Scientists have some theories. Maybe it's made of particles we haven't discovered yet. Maybe it's something called WIMPs, or weakly interacting massive particles. Maybe it's axions. Maybe it's something we haven't even thought of. But whatever it is, it's there. We can measure its effects. We can map it. We just can't see it or touch it. And then there's dark energy. This makes up about 68% of the cosmos. Dark energy is even weirder than dark matter. It's not a substance exactly. It's more like a property of space itself. And what it does is push things apart. Back in the 1990s, scientists expected to find that the expansion of the universe was slowing down due to gravity. Instead, they discovered it was speeding up. Something was counteracting gravity on cosmic scales and causing space itself to expand faster and faster. That something is dark energy. We don't know what it is. We don't know why it exists. We just know that it's the dominant force shaping the large-scale structure of the cosmos. So let's recap. 5% normal matter, 27% dark matter, 68% dark energy. Humans have built civilizations, art, science, philosophy, all based on that 5%. We're living in a cosmos where we only understand a tiny fraction of what's actually there. Mind-blowing, right? Within that 5% of normal matter, you've got stars, planets, gas, dust, black holes, neutron stars, all the things we can actually observe and study. Stars are basically giant nuclear fusion reactors. They take hydrogen, crush it together through gravity, and turn it into helium, releasing enormous amounts of energy in the process. That's what makes them shine. Planets form from the leftover material around stars. Rocky ones like Earth close in. Giant gas planets like Jupiter farther out. Black holes form when massive stars collapse. They're regions of space where gravity is so intense that not even light can escape. Neutron stars are the collapsed cores of massive stars, so dense that a teaspoon of their material would weigh billions of tons. And between all these objects, mostly empty space. Vast, unimaginable amounts of empty space. But even that empty space isn't truly empty. It's filled with quantum fields, virtual particles popping in and out of existence, radiation, cosmic rays, all sorts of weird quantum stuff. The cosmos is way stranger than it appears. Alright, so we've talked about what the cosmos is and what's in it. Now let's talk about where it came from. And this is where we get to the Big Bang. Now, the Big Bang is probably the most misunderstood concept in all of science. Most people picture it as an explosion in space, like a bomb going off. That's not what it was. The Big Bang was the expansion of space itself. It wasn't an explosion into existing space. Space, time, matter, and energy all began in that moment, or at least as far as we can tell. About 13.8 billion years ago, everything we can observe was compressed into an incredibly hot, incredibly dense state. We're talking temperatures of trillions of degrees, densities beyond anything we can recreate. And then it expanded, rapidly. In the first fraction of a second, there was a period called cosmic inflation, where space expanded faster than the speed of light. Now, that sounds like it violates physics, but it doesn't. Things in space can't move faster than light, but space itself has no speed limit. During inflation, the universe grew from smaller than an atom to potentially billions of light years across in less than a second. As it expanded, it cooled. Energy turned into matter. The first particles formed. Quarks, electrons, photons, all the building blocks of reality. Within the first few minutes, the first atomic nuclei formed, mostly hydrogen and helium, with a tiny bit of lithium. But it was still too hot for atoms to stay together. The universe was a plasma, a soup of charged particles and light bouncing around. For about 380,000 years, the universe stayed this way. Then, it cooled enough for electrons to bond with nuclei. Atoms formed, and for the first time, light could travel freely through space. That light is still traveling today. We can detect it. We call it the cosmic microwave background radiation. It's the afterglow of the Big Bang, and it's everywhere. If you could see microwave radiation, the whole sky would glow with it. After atoms formed, the universe entered a period called the Dark Ages. No stars yet, no galaxies, just clouds of hydrogen and helium slowly drifting through space. But gravity was at work. Denser regions began to pull in more matter. Over millions of years, these regions became denser and denser. Eventually, they became dense enough for fusion to begin. The first stars ignited. Light returned to the cosmos. These first stars were massive, short-lived, and contained no heavy elements. They lived fast and died young, exploding as supernovas. And those supernovas? They created the first heavy elements: carbon, oxygen, iron, gold, all forged in the hearts of dying stars and scattered across space. New generations of stars formed from this enriched material. Galaxies assembled. Structure emerged. Over billions of years, the cosmos evolved from a smooth, uniform state to the rich, complex, structured reality we see today. And we're still here, watching it happen, trying to understand it. Pretty incredible when you think about it. Let's zoom back out and look at the big picture, the overall structure of the cosmos. Because the universe isn't just randomly distributed matter, it has structure, large-scale structure. Galaxies aren't evenly spread out. They cluster together in groups and clusters. Those clusters form superclusters, and superclusters connect in a pattern that looks kind of like a cosmic web. Imagine a three-dimensional spider web made of galaxies, long filaments of matter stretching across hundreds of millions of light years, connected at nodes where galaxy clusters sit. Between these filaments, vast empty voids, regions of space with almost nothing in them. This is the cosmic web, and it's one of the most beautiful structures in nature. Why does the cosmos have this structure? It goes back to the early universe. Tiny quantum fluctuations in the first moments after the Big Bang created slight variations in density. Denser regions had slightly more gravity. They pulled in more matter. Over billions of years, this led to the formation of the cosmic web we see today. Dark matter plays a huge role here. It formed the scaffolding. Normal matter fell into the gravitational wells created by dark matter and formed galaxies. When you look at the largest scales, the cosmos is remarkably uniform. Look at a cube of space, 1 billion light-years on each side, and it looks pretty much the same as any other cube that size. Cosmologists call this the cosmological principle. The idea that on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in all directions. This is actually really important for physics. It means the laws of nature are the same everywhere. An electron behaves the same way here as it does in a galaxy 10 billion light-years away. Within this large-scale uniformity, you get local complexity. Galaxies come in different shapes and sizes: spirals, like the Milky Way; ellipticals, which are more blob-shaped; irregular galaxies that don't fit neat categories. Within galaxies, you get stars, nebulae, star clusters, all sorts of structures. And within star systems, you get planets, moons, asteroids, comets. The cosmos is structured at every scale, from the quantum realm to superclusters. There are patterns, there's organization, and we're still mapping it, still discovering new structures, still finding patterns we didn't expect. Every few years, astronomers discover something that challenges our understanding. A galaxy that shouldn't exist, a void that's too empty, a structure that's too big. The cosmos keeps surprising us. Now let's talk about what actually runs the show, the fundamental forces of nature. Everything that happens in the cosmos, from the smallest interaction to the largest structure, is governed by four fundamental forces. Let's start with the strongest one, the strong nuclear force. This force holds atomic nuclei together. Protons are positively charged, and positive charges repel each other. So why doesn't every nucleus fly apart? The strong force. It's incredibly powerful, but only works at extremely short ranges. Within an atomic nucleus, it's strong enough to overcome electromagnetic repulsion and bind protons and neutrons together. Without the strong force, atoms wouldn't exist. Stars couldn't fuse hydrogen into helium. The cosmos would be very different. Then there's the weak nuclear force. This one is responsible for radioactive decay and certain types of particle interactions. It's called weak because it's, well, weaker than the strong force. But it's still crucial. The weak force allows the sun to shine. It governs how neutrinos interact with matter. It played a key role in the early universe. Next up, electromagnetism. This force governs anything involving electric charges or magnetic fields. It holds atoms together. It creates light. It's responsible for chemistry, for how molecules form, for how your eyes detect the screen you're reading this on. Electromagnetism is way stronger than gravity, but it comes in positive and negative charges that tend to cancel out. So, on large scales, gravity dominates. And that brings us to gravity, the weakest of the four forces, but the one that shapes the cosmos on the largest scales. Gravity is universal. Every piece of matter attracts every other piece of matter. It holds planets in orbit. It holds galaxies together. It's responsible for the large-scale structure of the cosmos. We actually don't fully understand gravity yet. Einstein's general relativity describes it brilliantly as the curvature of space-time. Massive objects bend space and time around them, and other objects follow those curves. But general relativity doesn't play nice with quantum mechanics. We don't have a complete theory of quantum gravity. It's one of the biggest unsolved problems in physics. These four forces, working together and sometimes competing, create everything we see. They govern the behavior of the cosmos, from the Planck scale to the scale of superclusters. And here's something beautiful. The forces seem to be perfectly balanced to allow the cosmos to be interesting. If the strong force were slightly weaker, stars couldn't form complex elements. If it were slightly stronger, hydrogen wouldn't exist. If electromagnetism were different, chemistry would be impossible. If gravity were stronger, stars would burn out too quickly. If it were weaker, they'd never ignite. The cosmos seems fine-tuned. Now, this doesn't necessarily mean anything mystical. It could just be that we happen to exist in a universe where the constants allow for life, and in other universes with different constants, there's nobody around to wonder about it. But it's still remarkable. So we've talked about the cosmos, its scale, its contents, its history, its structure, and the forces that govern it. Now, let's talk about us, about life. Because here's the thing, as far as we know, life is incredibly rare. It might only exist on Earth, or it might be common throughout the cosmos. We genuinely don't know. We know life exists on at least one planet, ours. And we know that the raw ingredients for life seem to be common. Water exists on many worlds. Organic molecules have been found in comets, asteroids, and even in the clouds between stars. The question is whether chemistry ever crosses that threshold into biology elsewhere. We're looking. Missions to Mars are searching for signs of past or present life. Future missions will explore the icy moons of Jupiter and Saturn, which might have liquid water oceans beneath their surfaces. We're listening for signals from other civilizations. The search for extraterrestrial intelligence has been going on for decades, scanning the sky for radio signals or laser pulses that might indicate technology. So far, nothing. Silence. This is sometimes called the Fermi paradox. If the cosmos is so vast, with so many stars and planets, where is everybody? Maybe life is rare. Maybe intelligence is rare. Maybe civilizations destroy themselves before they can spread. Maybe interstellar travel is just too hard. Maybe they're there, but we're not looking in the right way. We don't know. But even if we're alone, we're part of the cosmos. We're made of atoms forged in stars. The calcium in your bones was created in a supernova. The iron in your blood was synthesized in a dying star. You are literally made of stardust. We all are. And we're the part of the cosmos that can understand itself. Through science, through observation, through mathematics, we've figured out where we came from. We've traced our history back to the Big Bang. We've understood the forces that govern reality. In a very real sense, the cosmos has become self-aware through us. Whether there are other civilizations out there doing the same thing, we're still part of something vast and ancient and beautiful. All right, we've covered a lot in the last hour. Let's bring it home. What is the cosmos? It's everything. It's 13.8 billion years of history. It's 93 billion light years of observable space, possibly infinite beyond that. It's hundreds of billions of galaxies, each with hundreds of billions of stars. It's mostly dark matter and dark energy, things we can't see but know are there. It's governed by four fundamental forces that work in perfect balance. It started in an unimaginably hot, dense state and has been expanding and cooling ever since. It has structure on every scale, from quantum fluctuations to superclusters. And somewhere in all of this, on a small rocky planet orbiting an average star in an ordinary galaxy, there's us, conscious beings made of stardust, trying to understand the whole thing. The cosmos is both humbling and empowering. Humbling because we're so small, so brief. Our entire civilization is a blink in cosmic time. But empowering because we can understand it. We've figured out so much. We've sent spacecraft beyond our solar system. We've detected gravitational waves from colliding black holes. We've taken pictures of galaxies forming when the universe was young. We've looked deep into the nature of reality and found quantum mechanics, relativity, the Big Bang, evolution, all these profound truths about existence. And we're not done. There's so much we don't know. What is dark matter? What is dark energy? How did life begin? Are we alone? What happened before the Big Bang? What will happen in the far future? These are questions we're actively working on. The cosmos is still revealing its secrets. So the next time you look up at the night sky, remember that you're not looking at some separate thing out there. You're looking at home. The cosmos isn't something we're in. It's something we're part of. Every atom in your body was once part of a star. You're intimately connected to everything out there, and that's pretty amazing. Thanks for watching. If you enjoyed this deep dive into the cosmos, hit that like button, subscribe for more content like this, and let me know in the comments what cosmic topic you'd like me to cover next. Until next time, keep looking up, keep wondering, keep exploring. The cosmos is waiting.